Very good. So I'm starting today with a couple of questions from the last section. What are the values of W, Z, and M? But, again, some of you should always be asking the question, why am I studying this? And again, a lot of this is based on data collection. And if I collected a whole bunch of data and it looked like that, you might say, hey, wait a minute, that looks like a line. And that's why we studied lines. Just like we had data that may have looked, the trend was going down and then all of a sudden it's going back up and somebody's going to say, hey, wait a minute, that sure looks like a quadratic. So it's all these graph ideas of what's going on. And of course, exponents, we started somewhere and it just starts growing really fast. Not as fast as a quadratic, but I have some kind of pattern like that going, and we talked about that being exponential, and I might have something that looks like this, and that doesn't look like the line or the U shape for a parabola, but this was a logarithmic. So it's these trends of studying data that have created all these equations that we have. Okay, so we have this study of logs and exponents, but these guys are related. How are they related? Well, we said they're inverses of each other. And a lot of this is all really kind of starting to tie together. If I take a look at this first problem, I cannot solve that yet. End of today, I can solve that. But right now, I can't solve this as a log. I don't know what that value is. But by turning it into an inverse, rewriting it as an exponent, I get base 3. So it's the base with an exponent of W equals 81. And of course, 81, well, maybe not of course, 81, fortunately, is 3 to the 4th power. So for the first one, I end up with W equals 4. Same idea. 8 to the Z power equals 8, which is really 8 to the 1st. Z would equal 1. So that's kind of one to tuck away. If the base and the number beside it are the same, it ends up equaling 1. Okay, do enough of these and it's going to really jump out at you. This guy had a name. It was called the common log. And if there's no base there, the base is 10. It's the one that's used the most. It's the common log. And 100 is 10 squared, so M equals 2. M equals 2. All right. So going back, just looking over some things from the last section to get us moving into this section. Now today we're going to start with working with logs. Now I'm going to read the title, and in this one, okay, so there's a whole bunch of properties that go along with logs. And the reason we have these properties is that sometimes we may need them to solve a problem. And you saw how math being a sister or a partner discipline, we learn the basics and then you apply it to another course you may have. But we have 3 properties here. First one is called the product. Okay. The log of a product equals log of the first plus log of the second. Well, I'm going to jump right into this guy down here and say, yes, this is common log of 2xy. That's going to be the same as log 2 plus log x plus log y. So I can take this and split it up, or I can actually use the reverse of this property. I can reverse it. If I'm giving something along these lines, I can reverse it back over there. And I'm going, yeah, okay, this isn't too bad. Log base 2 of 2 plus log base 2 of x plus log base 2 of y. And I'm even going, hey, oh yeah, we just talked about that. I could even simplify that to 1 plus log 2 of x plus log 2 of y. Down here, I have the natural log of a product, natural log of 3 plus natural log of the second item. That I can't touch. I have the log of a product, but I don't have a rule for the log of a sum. Saying that again. I have a rule for the log of a product, the product. And I have one for the quotient, which we're going to talk about next. But I don't have one for the log of a sum. I let that go. I can't touch that. Somebody say hammer time. Can't touch this. No. Okay, I guess I'm not done. Quotient property. Instead of multiplying, what if I now want to divide? Can I rewrite a log of x over y? And the answer is yes. It's the log of the first minus the log of the second. So when I come down here to number 4, I'm just writing, yep, this is a log of base 7 of z minus the log base 7 of 49. I'm going, ooh. I can keep going with that one. Because if I thought of this as separate, this is 7 to the what power equals 49. What does that become? See, this is maybe why I need to wait more often, because I'm not feeling the love here that you're understanding it, which carries over the test. It's hard with these remote classes when I don't see
2.
2. Yes, it is in fact 2. Very good. 7 to the x power equals 49. This guy is 2. Over here, I have log base 7 of a minus log base 7 of 14. 14 is not really a power of 7, so I'm not going to mess with that. And finally, here I have the log of 100 minus the log of the denominator, which is x plus y. Again, I have rules for the log of a product, which we just did, and for quotient, but I don't have the log of a sum. Not happening. This third rule is kind of helpful as well. It's the power property. And it says if I have log base b of x raised to a power, as bizarre as this seems, I can bring the power around front. Oh yeah? So this is actually the same as 5 natural log of x. 5 natural log of e, and that's something, because natural log, this is the same as 5 log base e of e. We've been looking at that. Log base e of e would be, remember, just hold that space bar down. You can temporarily unmute. What is log base e of e? E to the what power equals e. 3-letter word.
1.
1. Yes. So this becomes 5 times 1. The answer here is just 5. Yeah. Natural log of e is in fact 1. Let's see. I'm going to clean this up a little bit. This is actually log of x squared to the 1/3 power, which I know my rules for powers. A power raised to a power is the same as multiplying them. Now I have that exponent, 2/3 log of x. Oh, that makes things a little easier to work with. Any questions on the first page? All right. Oh boy. I have a whole second page. Lots of good problems. All right. Looks like everybody's back. I did jump around the room. Some were having active discussions. And like I said, all I wanted you to do is be asking, checking each other's answers. And, anyhow. The first one, log base 3 of 5 plus log base 3 of z minus log base 3 of w. Not sure how many you got to do. Next one, I have 2 in the numerator. Log base 7 of a plus log base 7 of c. I have 2 in the denominator, so I did minus, put these guys in parentheses because they are actual product, log base 7 of 5 plus log base 7 of d. Any questions on the first 2? All right. The next one is a product, log of x squared plus log of y. Then by the power rule, I can bring that 2 to the front. Take the squared and make it a coefficient. Again, reminder what the directions say. Write the expression as the sum or difference of logarithms. The next one, I needed to do a little cleanup first. That becomes x squared, because it's x squared to the 1/3 power, giving me 2/3. So it's going to become my numerator, which is natural log of 2/3, but I know I can swing that 2/3 around. Minus natural log of w plus z. This isn't a product, it's a sum. I can only split up a product. You got 13 right, that's a good job. That's a good job. Okay. If you got those first 4, you're in a good place. If you got the next 2, you're in an awesome place. Log base 2 of all of this is like all of this raised to the 1/2 power. So the first thing I did is bring the exponent to the front and get 1/2. Now inside I have log base 2 of 4x. So log base 2 of 4 plus log base 2 of x, that's my numerator, minus, and in my denominator, I have log base 2 of y, these are products, plus 3 times log base 2 of z. Got a little bit going there with the square brackets and parentheses. Again, this is my numerator, and this is my denominator. So really it should be minus log base 2 of y minus 3 log base 2 of z. And somebody might even say, wait a minute, I can take log base 2 of 4 and rewrite that as 2. Because 2 to the what power equals 4, 2 to the second power. You didn't have to in this case, but that's what it would be. One more. Log base 8 of everything in the numerator minus log base 8 of everything in the denominator. And again, I put this in parentheses. Log base 8 of 64. Yeah, I could actually change that to 2 if I want, because 8 squared is 64. Then I had x squared, but I brought the 2 around front by the power rule. Then I had log base 8 of y. Minus log base 8 of 3 plus log base 8 of z. And again, I swung that exponent around front using the power rule. 3 times log base 8 of w. Whoa. Any questions on page 2?
So while doing inverse one, same rule will apply from the regular logarithm, right?
So if I started on the right side,
Yes.
and that's the next page. We're going to start on the right side and use the rules to get back to what we start with over here. So we're going to take something huge and simplify it. I can't wait. There it is. Log. My numerator is 4x minus 3. My denominator is x. I'm done. I put those back together. I rewrote it as a single log. Before I start, I can say, hey, yeah, I'm going to bring that up to here. Now it's a plus log base 2 of z y to the 4th. That's not so bad. This is a plus, so I have z and y to the 4th. All right. I don't want to give you too long. I don't want people to get frustrated and give up. But let's see what we have. First thing I did is the power rule. I brought 3 up, made it the exponent. I have a term and I have a term. When it's plus, it's natural log of x cubed times x minus 2 divided by 5. I rewrote it as a single log. Now the next two get a little harder, but let's see. This is not 2 times a log, it's 2 times a difference in here. So the first thing I did was I distributed the 2. I distributed the 2. I came over here and took the 2/3 power up and minus natural log of z. This becomes the natural log of x squared minus natural log of x to the 4th. 9 times 2 is 18 divided by 3 is 6. And that stays as is. X squared is in the numerator. X to the 4th is in the denominator. Z to the 6th is in the numerator because it's plus. Minus, put z in the denominator. X squared over x to the 4th is x squared. Z to the 6th over z is z to the 5th. So that big honking ugly yada 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 does clean up pretty nice.
These are a little harder.
Yes, yes. And if you're following what I'm saying, that's a big help because you now
Yeah.
have good examples to look back at. Or if you figured them out by yourself, first try, awesome sauce. The -2 goes up, becomes my exponent. Don't really need to mess with that. And this is a difference. I have no rule for the log of a difference, so I let that alone. Let's see what I have. The log of, this is in the numerator, plus this is in the numerator, plus this is in the numerator. This is a negative exponent, so I put it down in the denominator. So I'm left with x times x squared minus 25 over x plus 5 squared. And I could actually go a little farther if I wanted, but we're actually working on these properties, so we're going to let those go. Questions up to 20. Questions up to 20.
So a product rule for the log and inverse is same, right?
Yes.
Okay.
Yep. We're just going in reverse. Instead of a single log, we have multiple logs and vice versa. Okay, we have a little puzzle kind of thing going on here. Log base b of 21. Well, I know what the log base b of 2 is. I know what the log base b of 3 and the log base b of 7 is. I know those values. So if I want the log base b of 21, I'm going to say, wait a minute, that's the same as log base b of 3 times 7. That's the log base b of 3, because I do have a product rule and a quotient, plus log base b of 7. So now we'll go get those values and add them together. 0.6826 plus 1.2091. I'm not going to grab my calculator to do that. You're all capable of doing it. But I was able to take something I didn't know and rewrite it. I have 2, I have 3, and I have 7. 21 I broke apart as 3 times 7. 9, I'm going to do this. This is the same as log base b of 3 squared. 2 times log base b of 3. Isn't that clever? Yeah. 2 times 0.6826. And again, I'm not going to grab my calculator. Let's see. We used the product rule. We just did an example with the power. Yeah, this one's the quotient. Log base b of 7 minus log base b of 2, 1.2091 minus 0.4307. And again, whatever that would be on the calculator.
In 22, will not have power 3 here for that point. At the last step.
Here?
Yeah, log b value is 0.6, so we're not gonna have 3 power here for that number.
No, because that's base b to the 3. Excellent thing, excellent point. I want to show you something real quick. Thank you. This is log 3 of b. Okay, there's no exponent. This is common log 3 with the power of b. This guy becomes b times the common log of 3. Yeah, so how students write this could become real sloppy, because this isn't a power, this is the power.
Yeah, that's the power.
This is base 10, that's to the first power kind of idea. So if I got ready and said, yeah, everybody, it's log base 3 of 6, And you're not, I don't know if that's the base or is 10 the base. So that's one thing to be careful of. Thank you for asking that.
You're welcome, but okay.
But yes, this last one, that's log base b of 3 to the second power. Swing your partner, swing that 2 around front. This is still log base b of 3. Mine started to get a little sloppy.
Okay, I wrote it wrong. That's why.
Yep.
Okay.
Yeah, okay. Last thing, this last thing is kind of really powerful. I like it. I love it. And it says, I don't know what it says. Well, it says this. What if I had this problem, log base 7 of 15? I don't know how to do anything with that right now. I don't know how to calculate its value. I don't know what's going on. But what it's saying is there's this another property up here, change of base formula, change of base. And if I take a look at this, I'm looking at right here. And what that says is this. I can rewrite log base 7 of 15 as the log, natural log, or excuse me, the common log of 15 over the common log of 7. Why is that an advantage? I can put this in my calculator. This can go in my calculator. Now, for kicks and giggles, I have log base 7 of 15 equals x. This is where it comes from. If I change that log into an exponent, I get 7 to the x power equals 15. So far, so good. Now, there's something that says if I take the log of one side, I have to take the log of the other side. So if I do that, I get the log of 7 to the x power equals the log of 15. Okay, this is what I started with. I rewrote it as an exponent, took the log of both sides. Now that I have a log, my power rule comes into play. X log of 7 equals log of 15. And if I said, okay, I'm going to divide by log of 7, I end up with a log of 15 over log of 7. Which means those two guys are the same. Log base 7 of 15 is the same as log of 15 over log of 7. I took this, rewrote it as an exponent. 7 to the x power equals 15. Took the log of both sides, brought my exponent around, divided by the log of 7, and boom, there I am. So what can I do? I can now do this on the calculator. I can go in and I'm going to do this one while I'm here. I'm going to say the log of 15, and I'm going to hit enter, divided by the log of 7. Hit enter, 1.392. Okay, it's called the change of base formula. We derived it, so we know that it's cool, it exists. Log of 0.3 over the log of 5. Again, putting it right in the calculator. Log of 0.3 divided by log of 5. Negative 0.748.
So while showing the work, how much we are going to just stop in the second step?
So we do the quick change. We go from here to here.
Yeah.
Now we can put it in the calculator and find the
Okay.
value.
Okay.
It's funny, they say 4. We've been doing 3 decimal places. So if it was actually on the computer, we'd have to follow it implicitly. So putting the 4 decimal places so we can get it right, even though everything else was right. But that's how we do it. Questions? Questions, questions, questions.